So for triple integrals in spherical coordinates, first of all, we need to describe what what a spherical coordinate system looks like. So this one is going to be a bit more elaborate rather than the polar or its 3D version, which is the cylindrical. So let's see. So well, let's talk about the different features here. So okay, second. So the spherical coordinate system is mostly used when we're integrating over spheres, where our regions of it, so our solid regions of integration are spheres. But it's not limited to just spheres because later we will see how we can change a lot of the equations or a lot of other situations that can potentially not have anything to do with circular shapes, cylindrical, parabolic, or cones. Well, so what we're going to do here is describe what are the three coordinates. Well, so here we're going to go from a point x, y, z to a point rho, phi, and theta. What are these three symbols? Well, rho will represent the radius of the sphere. It's not going to be the same as the radius of the circle because a sphere, again, will project a circle on any plane, not just the xy plane, but also the yz plane or the xz plane, depending on what's your perspective. Well, but typically we do the projection onto the xy plane. Well, so that's going to be a different radius. We'll check the difference in a few more minutes. Well, then we're going to have two different angles right here. Well, the theta angle that you guys are already familiar with, that's the same angle as what's that? That's the same angle that we did back in polar coordinates, and we call this the polar angle. Now we have another angle that it's called phi. That's what we typically call the drop down angle, but formally it's called the azimuthal angle. What is that angle? So that is the angular distance that goes that goes from the North Pole all the way to the South Pole. That means essentially this angle, because it's called the drop down angles, if you are at the North Pole, so it's going to do this all the way to the South Pole, spanning a total angle of pi or 180 degrees. So animations that we're going to look at later are going to help us see this idea about the drop down angle a lot better. So, and again, theta, it's the same as in cylindrical coordinate. That means theta goes between 0 and 2 pi. All right. Well, so let's discuss where is this system coming from. Well, here's the conversion formulas in a similar way that we had, like r cosine theta and r sine theta for for the polar and the cylindrical coordinate system. We'll have conversion formulas to go from spherical to rectangular and vice versa, and to go from spherical to cylindrical and vice versa, because we may need to go between one system and the other among the three systems that we have been discussing. All right, so I'll show you where are these formulas coming from. So they look big, they look complicated, but this is just a result of using basic trigonometry. And for this, we're going to use the images below. So again, what do we have? Number one, we have the radius rho, which again, it's not the same radius of the circle. So that's the distance from the origin to any point on the sphere. So here we have the around angle, which is the polar angle, goes between 0 and 2 pi in a similar way in cylindrical and polar. But again, this drop down angle phi goes between 0 all the way down to phi. That is from the North Pole all the way to the South Pole. It is measured as an angular distance. So, well, let's get the armor of that solid, so to speak.
Why is that length rho? Why is it not the same length as the radius of the circle?
Because that's a good question. Because if you have this rho right here, you are projecting only this circle right here, not the circle with the same radius as the sphere. If you have this other point only here, if you would be projecting only this circle. So r is the radius of the circle projected on a given plane, but rho is the radius of the sphere. So it's two different. So okay. Let's make this picture look a little more 3D. So to facilitate the visualization here, so I'm going to highlight this part with green, and I'm going to highlight this part with yellow. All right. So this situation right here is going to give rise to two right triangles, for which we're going to do SOHCAHTOA to get the conversion formulas. Okay, so let's label. Of course, I mean, this is x, this is y, all right? This is the height z, all right? X, y, z. For a second, forget about the spheres, the circle. Let's look at this as x, y, and z. That's it, all right? Now, this little r right here, that little r right here is the radius of a potential circle that gets projected depending on the point. Okay, let me get rid of this part because I need it. All right, and well, of course, this rho right here is this distance from the origin to a point P on the sphere. Okay. Let me do a couple of right triangles. So let me draw this right triangle in green, so it's easier to see. That is x, y, and r. All right. So let me highlight it with green so you can see where am I getting this triangle. And this is going to be the reference angle. Notice this angle theta, which is going to be the polar angle, not the azimuthal angle. The angle that goes around the sphere, not from the North Pole to the South Pole. Two different angles here. All right. So that's one triangle, and I'm gonna do SOHCAHTOA for this. So on the one hand, so you know the formulas that are in this case x equals r cosine theta, and y equals r sine theta. However, just note that these conversion formulas right here do not depend on r at all. All right, do not depend on r. So somehow we need to replace this r lowercase r with terms of rows. Okay, so for this, I'm going to use the yellow triangle here. So I'm going to draw it again. I'm going to draw this on the side. So this is the angle, and let me color in yellow the same way. And well, let me just do this dashed vertical axis, the z-axis, right? So just to give you a better perspective, so we're looking at this triangle right here from this direction, and so it's easier to see. Now, by equivalence of angles, so to speak, well, do you guys agree that this angle right here, isn't that the same as this angle right there? Isn't it the same? So this angle right here, that is going to be phi, right? Okay, what else do we have? Okay, this horizontal distance, which is r, right here, and this height, which is z, and from there I'm going to do another SOHCAHTOA for this triangle. All right? Okay, so let me do sine of, in this case, the angle phi, but be careful because the reference angle is at the top, it's not on the side like the green triangle. So opposite, which is r, over hypotenuse, which is, oh, in this case, that's rho, all right? Over rho, which means r, from here we can already get r equals to rho sine phi. And likewise, cosine, a little higher, I'm going to do that space. And also cosine phi is adjacent, which is z over rho, which means z equals to rho cosine phi. And we already have one of the conversion formulas, right? It's right here. That's z equals rho cosine theta. Now we need to get those for x and y. All right? So what are we going to do? Because remember how x and y here, they're in terms of r, that is in terms of the radius of the circle projected, not in terms of the radius of the sphere. And we need to write these conversion formulas in terms of the radius of the sphere because we're dealing with spherical coordinates, with spheres, no longer circles. That's polar or cylindrical. So I'm going to do the following. I'm going to replace this little r right here, there, and there, and see what's going to happen. So this is going to give us rho sine phi cosine theta, and over here rho sine phi sine theta. And this is how we get the other two coordinates. All right. Well, what about to go the other way around? I mean, to get the radius of the sphere, for instance, to get the radius of the sphere, that's really using the equation of the sphere, x squared plus y squared plus z squared equals rho squared. So just replace the r with a rho, all right? And if you take the square root on both sides, so that's really like finding the distance between 2 points in space, which is the radius of the sphere. That's the distance between the origin and any point on the sphere. The angle theta, it's still the relation, the tangent of tangent of the angle, it's still the ratio y over x. And this arc cosine, well, we can derive it from this relation here, because here cosine phi equals z over rho, but rho would be the square root on both sides, which is this expression here. All right, so we don't need to derive all of these formulas. Actually, these come up when we convert other equations, when we convert other points, which is what we're going to do right now. Convert the cylindrical coordinates points to spherical coordinates. Okay, so number one, let's write a sketch of what we're going to do here. So number one, so we're going to go from r, theta, and z, that's cylindrical coordinates, and we're going to go to, what's that? That's going to be rho, phi, and theta. All right? Rho, phi, and theta. What do we have? So far we have, okay, we're given 4 pi over 3, 4. And we're going to go, so here is the thing. We already have a given here because it turns out that the theta from cylindrical will be the same as the theta in spherical. That is the polar angle. All right, the angle that goes around the circle projected onto the circle projected onto the xy plane from the sphere. That is pi over 3. So we need to figure out rho and phi. How are we going to do that? Well, so we know r in this case, right? So this is r, theta, and z. So we could use the rho squared equals to x squared plus y squared plus z squared. Okay? We can use this relation to what? To go from r to rho. How do we go about that? Well, that's because, check this out. So we know that in cylindrical or in polar, x squared plus y squared, that equals to, isn't that r squared? Okay, isn't that r squared? Which means rho squared equals to r squared plus z squared. But hey, don't we have r and z on the given point? let's just substitute there, and that's going to be our rho. Rho squared equals to r, which is 4 squared, plus z, which is 4 squared. Rho squared equals to 16 plus 16, which equals to 32. Rho squared rather, but rho is the square root of 32. And simplifying this, that is 32 equals 16 times 2, that equals 4 root of 2. All right? So rho is 4 root of 2. Now we need to find the drop-down angle, the azimuthal angle, the phi angle. All right, how are we going to go about that? Well, so let's see. We have another relation because here we have a few of them. However, these may have too many terms or too many factors. Let's use the relation for z because we know the value of z and we also know the value for rho. So we can use that last relation and get the angle, the azimuthal angle. So that is cosine phi equals to z equals to rho cosine phi. So z in this case, which is 4, equal to rho, that is 4 root of 2 cosine phi. And let's solve for the angle phi. So let's divide both sides by 4 root of 2. Divide out, that's cosine phi equals to, divide out the 4's, that's 1 over the square root of 2. And well, what angle has a cosine equal to 1 over square root of 2? That's one of the special angles, isn't it? It's pi over 4, right? And that's pi over 4. Right? Problem. Okay, so let's convert the rectangular coordinates to spherical coordinates and then to cylindrical coordinates. Okay, so rectangular coordinates. So when it comes to converting from rectangular to either spherical or cylindrical, draw the point, or rather plot the point on the plane. But this point given is in space, not in the plane. That's fine. So that's because anyway we will need all these pieces of information that you're about to see. So that's just plot the x and the y in the xy plane. So that is 1, 2, 3, 4, 5. That's 0, negative 5. That is this point right here. Okay. And I think this point it's easy to convert to polar. And well, converting to polar essentially will be the same as converting it to cylindrical because x and y become r and theta, and z remains the same. That doesn't change. So, and in this case, well, if we want to convert from x, y, z to r, theta, z. Okay, so the z is already a freebie here. It's already given. That is 4. All right. But what about the other two? Okay, this point right here, 0, negative 5. So let's look at the angle. In this case, we don't need to use any of the trigonometric relations because I think this angle is pretty obvious. Isn't that 270 degrees or 3 pi over 2? Right? So the angle is theta equals 3 pi over 2. And then, what about the radius? Do we really need to do the square root of x squared plus y squared? How many units are there from the origin to this point? 5, right? Not negative 5. Yes, it's 5 below the x-axis, but as a radius r, there's no negative radii, right? So that's why we express it as a positive. Or if you're not convinced about that, just use the formula square root of x squared plus y squared. You should get a positive result. And that's our result in rectangular coordinates. All right? So now we need to convert this point to spherical coordinates. And well, I'm going to take the same approach I did in the previous example to go not from rectangular to spherical, but rather from cylindrical to spherical. Because otherwise it's gonna be a bit weird to do such calculations. So what are we going to do? So we need to figure out, well, the polar angle is already there, all right? We need to figure out rho, that's the radius of the sphere, not the radius of the circle, it's the radius of the sphere, which may or may not be the same. And we will need to figure out what? The azimuthal angle. Okay, we could figure out rho. Let's get rho first. That's the square root of x squared plus y squared plus c squared. All right. So rho, which is 0 squared, the square root of 0 squared plus -5 squared plus 4 squared. That equals, okay, the square root of, okay, that's 0 squared, that's 0, 25 plus 16, is that 41? That 41? Yes. That's the square root of 41. Okay? So that's rho. See how it's not the same as the radius of the circle? It's now the radius of the sphere. Now, what's next? We need to find the azimuthal angle, and although there's a few relations to find it, let's use the easiest one, which is z equals to rho cosine phi. Let me solve for the angle first. Cosine phi equals to z over rho, where in this case cosine phi equals, what's z? Isn't that 4? Over rho, which is the number we just found, that is the square root of 41. Now, if we take the inverse cosine to find out what the angle is, phi equals to arc cos of 4 over root of 41. Since in this case, this ratio of numbers is not one of those special ratios that would give us, say, 45 degrees, 30, 60 degrees, or their multiples in the different quadrants. Let's just leave it in exact form. All right? So that means we're going to go from and express this point x, y, z in spherical, rho, phi, and theta. That is 0, -5, 4. What's rho? That's the square root of 41. Oh, I'm gonna need more space in here, I think. Okay. And phi, that's the drop down angle arc cosine of 4 over the square root of 41. And the angle theta, which is the same 3 pi over 2. It's the same angle as in the cylindrical or polar, if you will. In the end, we call it the polar angle. All right. So that's as far as converting points between one system and the other system in a similar way that we went from, what was that? Polar to rectangular and vice versa. Polar to rectangular to cylindrical and vice versa, as we did yesterday. And well, today we introduce a new one, spherical coordinates. Now, here is the thing: when it comes to setting up double and triple integrals in spherical, we may need to do a lot of transformations of equations. So, in this case, then we will need these relations that we have in the definition box in the previous page to convert these equations. For instance, we need to get some practice on how to convert equations of planes. But I mean, if you wonder, well, why do we want to convert equations of planes if we're dealing with spherical coordinates? That it's a more round or circular looking shape? Well, actually, there's situations where either the floor or the roof of a solid over we're going to integrate, it's going to be a plane. So it's yes, even though spherical coordinates are, it's usually our best choice to integrate over, of course, spheres. What else? Cylinders and cones, not parabolas. So for I mean paraboloids, for paraboloids, the best choice is what's it called? It's a cylindrical system. So we still need to deal with these planes and all that. All right. Let's convert the equations of these planes x equals 4, y equals 3, z equals 8 into spherical coordinates. How are we going to do that? Well, we're going to use the relations we have in the previous page. So what is x equals to? Replace x with the quantity rho sine phi cosine theta, and so rho sine phi cosine theta equals to 4. And solve for the variable rho in this case. That is, divide both sides by sine phi cosine theta. Rho equals sine phi cosine theta in the denominator of 4. But well, you may not want to leave variables in the denominator, so you might want to use trigonometric identities and move this sine phi to the numerator and cosine theta to the numerator. That is, rho equals to 4 cosecant phi secant theta. And that's how an equation of a plane looks like in spherical, right? Yes, it looks more complex, more complicated than just x equals 4, y equals 3, z equals 8. But yes, we need to get used to these conversions. What about the equation y equals to 3? We're going to do one of each. One in the x direction, one in the y, and one in the z. So we need to identify our conversion formula for y. Let me go back to the previous page. And so y equals rho sine phi sine theta. So rho sine phi cosine theta equals to 3. In a similar way, divide both sides by sine phi cosine theta. That's going to leave us with the rho equals to sine phi cosine theta in the denominator of 3. And again, move this to the numerator using trigonometric identities. That is 3 cosecant phi secant theta. And lastly, z equals to 8. This one is going to be a lot more simpler, or compact, if you will, rather. So here, let me go back and find out what's the relation for z. So for z, that's rho cosine phi. So that's rho cosine phi equals to 8, and rho equals to 8 over cosine phi. And we should just move rho equals to 8 secant phi. Alright? Yes.
Isn't y sine phi sine theta?
Oh yeah, that's sine. That's sine. That's correct. That's sine, sine, and that's also sine. And that becomes cosecant, right? Another cosecant. Thank you. Yeah, that's cosecant. Alright, so that's how we convert equations of planes. Because we're going to need them for later, for a set of problem we're going to do. You're going to need this for today's take-home quiz as well. Alright? So, okay, let's write the equation of the cone. I mean, let's think about cones. So z equals to the square root of ax squared plus ay squared. So that's how a cone or a circular cone is going to look like. How do we know it's a circular cone and not an elliptical cone? That's because the coefficients of x squared and y squared, they are the same. If we were to work with, what's it called, with cones that are not circular, they're rather elliptical, then the spherical coordinate is not going to work. Then we would need the Jacobian to transform that that elliptical cone into a cylindrical cone, and then, or a circular cone, and then do the spherical coordinates again. But that thing about the Jacobian, that's going to come later, not right now. You'll see what it is about later. All right, so let's do the following. How about we square both sides to get z squared equals to ax squared plus by squared. All right? What am I going to do next? I'm going to use the relations for x and y. Actually, I have them in the so conveniently. I have them in the previous exercise. I have that for x right here. I have that for y. And I also have here that one for z. All right? And we're going to use them. Okay, so that's I'm going to replace those here, there, and over here. All right? Yes.
The question says AY squared instead of B.
Oh yes, it says A. So I don't know where the B came from. Yep, that's A. All right. Thank you. Okay. So let's replace z with rho cosine phi quantity squared equals a times some quantity squared, that is x, which is rho sine phi cosine theta quantity squared plus a times the quantity in yellow here for y, rho sine phi sine theta quantity squared. So let's do a lot of squaring here. So let's rho squared cosine phi squared equals to a rho squared sine squared phi cosine squared theta plus a rho squared sine squared phi sine squared theta. Yes, it looks big, but there's going to be a lot of simplification. It's going to simplify to something really, really nice in here. All right, so let's see. Number one, how about we factor common factors actually on the right hand side of the equation? Do you see how a rho squared sine squared phi is common to both terms? Okay, let me factor it out. A rho squared sine squared phi times cosine squared theta plus sine squared theta. Oh, what is that? Isn't that equal to 1? By Pythagorean identity, so that's where it simplifies a lot. So that's rho squared cosine squared, okay? So this simplifies to 1. So we no longer need to keep writing that. Okay? So we're going to be left with the following, that is rho squared cosine squared phi equals to a rho squared sine squared phi. And in this case, how about we divide out the rho squareds? And that's going to leave us with the relation cosine squared phi equals to, what's that? Sine squared phi. Oh, don't forget the a. So I'm going to do the following. I'm going to solve for, what did I do? Solve for a? Yeah, let me solve for a right here. So that is a equals to, or rather, let me do cosine squared phi over sine squared phi equals to a. Okay? So I know what you might be thinking. Cosine over sine, that equals to cotangent. But I'm going to use the tangent relation instead because it's going to be a lot easier. Let me continue on this side here. So I'm going to write this as a sine squared phi over cosine squared phi. But if I find the reciprocal on the left, I need to find the reciprocal on the right. That is 1 over a. Which in this case is sine over cosine, that's tangent, but that's a squared. Tangent squared phi equals 1 over a. And in this case, if I take the square root on both sides, that's going to give me tangent phi equals to the square root of 1 over a. I know what you might be thinking. I should use plus and minus because of the algebra, because of the square root property, yes. But in this case, we have limitations with the azimuthal angle, that is the drop-down angle. It can't be negative. It only goes between whatever goes the north pole all the way to the south pole, which is 0 and pi, or 0 and 100 and 180 degrees. So we're good to omit this plus minus. All right? So the square root of 1 is 1. The square root of a is just the square root of a. Okay? That is tangent of phi. That means the drop-down angle phi is the arctangent of 1 over the square root of a. All right? This formula to your sheet of notes. Right? We're going to use this formula a few times. Right now in some of the exercises, you guys are going to use it in the take-home quiz. And well, to show you an illustration of this, let's go about GeoGebra. Okay. All right. What about the simplest of the cones? What about the simplest of the cones? No, that's not what I wanted. Don't save. Okay. So, for instance, let me just draw a cone. Well, the equation of a cone, z equals to the square root of x squared plus y squared. All right? Let's graph this cone. How about that? We plot this cone in GeoGebra. So you want to see my keyboard? Okay, so that is z equals to the square root of x squared plus y squared. All right, so x squared plus y squared. All right. Well, so this is our cone in space, in 3D perspective, right? However, what if I wanted to find the traces of this cone? For instance, I just want to focus on, say, the YZ trace. Do you see that diagonal line? The angle is kind of obvious, right? The angle form is kind of obvious. What's the angle? 45 degrees, right? Or pi over 4. Okay, with all this formulation we just did, let's make it worth it. Use it to express that cone as an azimuthal angle, right? Or as a drop-down angle. For instance, what is a in this case? What's the number that multiply x and y? 1, right? So in this case, a equals to 1. Phi equals arctan of 1 over the square root of 1, which is arctan of 1. All right? That's the arctangent of 1. And what is the arctangent of 1? Right? Right? Did you see it? Pi over 4, or 45 degrees. Well, typically we use the radian mode. We don't go about, what's it called, the degree mode. Anyway, what about another cone? Okay. Let's see. Okay, let me put a 3 here. So a will be 3. All right. And I'm going to replace this with 1 over the square root of 3. And let's see how is that going to look like. Okay, let me go back to GeoGebra and see how is this going to change. Okay, let me put a 3 in here. That's a 3. And that's another 3. How does that look like? What's the angle? Pi over 6?
Over 3.
Some of you say pi over 3, some of you say pi over 6. Ah, that's a good one, isn't it? Okay, which angle are you looking at? The shaded one or the empty one? Which one are you looking at? Or I mean, which one are we supposed to look at? Huh? The shaded one, right? Because we're starting at the North Pole and we're walking towards the South Pole. Well, we're going as far as this angle, so we're looking at that angle, which looks like, which one is it? Pi over 6 or pi over 3? Pi over 6. Okay, well, yes, it's kind of obvious from the picture, but hey, we need to show this algebraically using this relation. Well, actually, I already set it up for you. What's arctangent of 1 over root of 3? Not theta. This is phi. Okay, that's pi over 6. All right. Should we do another one? Okay, for pi over 3, what should I do? I should have the reverse, I think, right? Okay, let me do 1/3. 1/3. I believe that's the one that's going to work. Let me see. Hopefully, because I'm trying to improvise a little bit here so you guys can see everything. Okay, so let me change this 3's for 1/3. 1/3. 1/3. Does that look like pi over 6? Yes, it's just gonna look wider, right? Does that look like pi over 6, the shaded angle? Yep. Okay. Let's see. Let's see about it. So A in this case is 1 over 3 or 1/3. So arctan of 1 over the square root of 1/3. Oh, this one is going to be a crazy one. This is going to be a complex fraction. Let's that's arctan of 1 over root of 3. Simplifying the complex fraction, this is the same as saying arctan of root of 3. What is arctangent of root of 3? Pi over 3, right? Does that agree with the picture, right? So that's one way to visualize this. What's it called? These cones right here. There's other cases that we could express using spherical coordinates. I did it last semester with the paraboloid, but I found out it was not worth it to show because in the end it gives a very complicated result. So we're going to skip the paraboloid case. And again, it's not the best choice for spherical coordinates. And anytime you have a paraboloid, just use cylindrical coordinates, right? That's the best choice. Okay, what else do we have? Okay, the integral. Should we do the integral?